So we are in part 2 of vehicular area networking, vehicular networks, VNets. Last time we talked about this diagram, and key thing to notice is that the area is covered by 3 different standard bodies. ASTM, for whatever reason they needed this thing first, so they started there. Then IEEE came up with 1609, and then they needed the physical layer, which was provided by the 802. So with that, basically the ASTM part covers more on the application layer issues, which are what are the different priorities in the messages, and how much power, etc. they should handle. The 1609 is mostly on the management and security, and 11, as we said, is mostly physical layer. So we go to the 5, and as usual, if anything is to be designed in these days and age, so there was actually a period when everything was CDMA. That is when 3G was developed, 90s. CDMA was the new thing, so the whole world went CDMA. Now it is OFDMA. Okay, so any new protocol that is developed, that you will see OFDMA, right? So right here, P is OFDMA, OFDM with 64 subcarriers in 10 megahertz. So we have seen this now enough times. 48 data, 4 pilots, 12 guards. Very similar to A, and subcarrier spacing is half of that in A. So that's another thing which is generally happening is that previously we started with subcarrier spacing so large, and as the electronics is improving, we can make that smaller and smaller and smaller. As a result, the data symbols can become larger and larger, and you have basically more throughput. So this one is half of 11A, and therefore because the spacing is half, if you remember from the last time, 1 upon T, the T is 1 upon the spacing. So if the spacing is half, the symbols are twice as big. All right? And so all the time parameters are doubled. Symbol size is twice. Guard interval is also twice. So what that means is they kept the guard interval at what value of the symbol size? Well, basically, if you don't remember 11A, you might remember in wireless HD, how much was the guard interval? Anybody remember what factor of the symbol size? 1/8. Good. All right. And so this is in that thing. I don't remember 11A myself. It could be 1/4 or 1/8. But anyway, so that number is still there. Okay. And so therefore, here there is one problem with compared to 11A in 11P. There is mobility, and because of mobility, the frequency is going to shift, right? Because of the Doppler effect. And if the frequency is going to shift, keeping close frequency is going to be tough, and also the guard interval will have same effect. So they could have actually argued for a larger guard interval, but anyway, the guard interval is same ratio of the symbol size, so guard interval is also twice. But in time, it allows more the rest, right? Now the data rate is half. Well, so what that means is they are not going for very high level modulation. Okay, in 11A they might have tried, let's say, 64 QAM. here they said probably we don't go that far. So that's why, because of all of this, the data rate is lower. So 27 megabits per second max. So by the way, I mean, this is T is a lowercase. What that means is both 11A and 11P are now in the same standard. If you download 11 standard, which is probably so thick, all 1300 pages, these are simply different subsections. You know, so 11A, this is the size. For 11P, this is size. Now they will not even use probably they will not use 11A and P there, but the sections might be numbered A and P, and you will see the same parameters being used. All right, any question about this phi? Okay. So let's compare. Frequencies are very close, not the same frequency band. FFC size is 64, data supply is 48, pilot supply is 4, channel width is half. Okay, so that is one reason the data rate is half, is the channel width itself. So that was not the modulation. Symbol duration is twice as much, guard time is twice as much, FFT period basically all twice, and the preamble is also twice. Anybody remember what is the preamble? Yeah? Okay. Actually they are not random. Some predetermined set of bits. Pretty good, basically, in the sense that what you do is you send some bits in the beginning, which are 10, 10, 10, 10, 10, 10, 10, 10, 10, or 111100. There's a predetermined set of bits that you send so that other people can synchronize. Right, but it is before the frame, preamble. All right, so this is 32 microseconds, so it allows you more time to synchronize. Okay. So now we saw there are 4 channels, and you need at least 2 channels, one for the control and one for the service. If you remember here, there were 4 these channels. Control channel was in the middle, and there were 4 service channels. So you need a control channel where it tells you what you can do and when you can do it. And so some devices will use, all devices use CCH and one or more SCH. Service channel. Multi-channel devices that can use CCH and SCH continuously, and single-channel devices, that means they have only one radio, and they can use either CCH or SCH to that radio, and therefore they need the time to switch between these 2 channels, and so there is time allowed for switching. All devices must monitor CCH. Okay? So this is like beacon. Everybody has to listen to beacon. So beacon is done on control channel. So basically you listen to that during that period, and there it says that, okay, now you can talk, or, now they can talk. And so all devices synchronize clocks to the UTC time, and everybody knows what is UTC. Huh? Huh? Universal time, and I forgot C, but basically universal time, this is basically what your computer is synchronized to. When you have a world clock, you have this automatic synchronization of time on your computer, that is basically synchronized UTC time. In Teams, we will put it basically UTC minus 6 hours, and in other countries it will be different. So everybody is on the same basically time, and this is a standard. This is nothing new here. I mean, this is basically everything in the world is now UTC synchronized, right? Generally, RSUs, which is the roadside unit, will have GPS clocks and transmit it in their beacons. So one way to get the time is through the internet, like your computer does. Another way is through GPS. GPS signal when you get, it not only tells you your location, but it also tells you time. The way basically it tells you time, and they say all it does is tells you time, not really your location. But if you get the time from 3 or 4 different satellites, you can figure out the distances from those satellites, and you can figure out your location. And so the way GPS works is that there's a satellite number and there's a time. Okay, and everybody knows the location of the satellites. And therefore, you can figure out I'm so far from this and so far from that, so far from that, and you draw circles, and wherever they intersect, you know that is where you are. Okay, so GPS time. So RSUs will have GPS. Actually, I would not be surprised now that the vehicles can have GPS. I mean, GPS is such a standard thing. Every little phone has a GPS, and nowadays they have about. I mean, just the last week they announced $5 smartphone, something like that, okay? If you can have a $5 smartphone and you can have a GPS in it, you know, the cost can certainly afford it. So GPS time is there. Wave basic service set. So now these are BSS, IBSS, TBSS, and this is W-BSS. The only thing to remember is that the TBSS corresponds to 802.11. What the letters? TBSS. Nobody is reading anything in the class to the class, and therefore I got to take exams after every class. TBSS. HD, which is AD, right? And WBSS is P. So don't get confused. TBSS has to do with AD, and WBSS has to do with P, 11P. So this is Wave Basic Service Set. Wave Basic Service Set. The W comes from Wave. And the neighboring BSS use different service channels. Okay, so there are 4 of them, and so you could have up to 4 overlapping wave sets. Now they have priorities actually. So 2 types of traffic, IPv6 and WSM. WSM is this one, and this is IPv6. So 2 kinds of traffics are coming in. WSM is the wave short message protocol, and IPv6 is the standard internet protocol. No IPv4 because of the addressing issues. So they decided not to use IPv4 because there are not enough addresses for the cars. WSMP packets, which is from the ASTM, they contain channel number, data rate, power level, and priority. Now you can see that IPv4 does not allow any of this, okay? But ASTM wanted to make sure that they can dictate how much power will be used to transmit this packet. IPv4 has nothing other than a destination. You have to figure out how much power to use. ASTM tells you the power level, it tells you the data rate, it tells you the priority, and it even tells you channel number. Okay. IPv6 stream need to inform MLME. MLME, if you, again, you have to go back to this diagram. MLME is right there. MAC Layer Management Entity. Okay. IPv6 informs MLME about their profile. Now the problem is because IPv6 directly cannot tell you about the channel number, data rate, and power level. It does it in the sideways, which means that somehow these applications tell the management, through the management, that this has to go this far, and this comes to the management channel, and then it comes here. Okay, so IPv6 streams. What streams means is applications here. Okay, IPv6 applications need to inform MLME about their profile. That includes, so when you have something going on, you set up the application tells the management that, look, I need to talk to a car which is 100 miles away, or actually not 100 miles away, half a mile away, and so power should be so much. 802.11e is extended to support 4 queues for each channel. Actually, I don't know what was the extension here, but okay, then. So the extension here is, in 802.11e, we have 4 queues already. But there is only one frequency band, only one frequency channel, right? Now they have 4 channels, so now there are 16 queues. So 802.11e is extended to support 4 queues for each channel. And channel router directs the packet to the right channel and queue. So that picture is coming next. Channel router and channel selector. Channel router directs the packet to the right channel and queue, and the channel selector monitors the channels and schedule transmission. So basically there are 2 people required. One is before the queues and one is after the queues. So when the packet comes in, the router decides where should the packet go. Okay? And when the channel selector decides who should get out. Okay, so really the priority is implemented here because the highest priority will go first. This one simply puts the people into the queue, and this one takes out actually packets from the queue. Channel selector and channel router. One is at the input to the waiting area, and one is at the output of the waiting area. Okay? Another point to notice is that on the control channel, IPv6 packets are all data packets, and so they go on the schedule in this one service channel. WSMP has both control and data in line. You see, when this was designed, they didn't think of the management channels. Everything comes from here. Whereas in the other cases, the management will come through here, right? So those are the things that go on the left side here, on the control. And all the data packets go here. So the WSMP packets go into 2 places. And depending upon the priority, they go to the right priority queue. Same thing, the control packets go into all these different places, and depending on the priority, and then they selected here. So how do you form a BSS, basic service set? Again, since there is no access point, actually there could be an access point, but in this case they decided, just like everything else we have seen so far, that it's a function, and any station can do that function. So WSS coordination function can be done by any station when requested by an application. So the provider is the device that starts WSS and generates the announcement. So this is the coordinator, and the coordinator could be either an OBU or RSU. Now, if you remember, what is RSU? Roadside unit. OBU is the onboard unit. So either the car or the tower can be a provider. And everybody else joins and they become the user. And if it stays persistent W-BSS announced every sync interval, so there is a period over which the announcement is made that, okay, I have this W-BSS. Non-persistent is whenever you need it, you start it and then you go away. Short-lived, announced at permission only, easy support to on-demand file download. So if you were either transmitting some files or you were receiving some files, then you will form a W-BSS, see if there is a car nearby or a RSU nearby, and then you can start communicating. Server applications registered with WME with a provider service identifier, PSID. So this is similar to SSID. Service set identifier, and this is PSID. And now this is confusing because they call it W-BSS, but the IDs are called PSID. Okay, provider service ID. So server applications registered with WME, but actually this is different than SSID. SSID is the name of the network, and this is like a port number. Okay, so it's like 80, 21, 23. These port numbers. So that port number really indicates what the application is. So when you want to talk to somebody, let's say you want to do the file transfer on the internet today, you will say, I want to connect to port 21. Okay? And at the other end, generally port 21 will connect to an FTP server. Alright, so that's the standard. It is quite possible that somebody has an FTP service on port 22. In that case, they will just let the people who are connecting to it that, look, you're going to connect to me, you will connect on port 22. So you send a message, I want to connect to port 22 on this computer, and you will connect to their FTP service. So there are well-known port numbers, and you don't have to use them though. So everybody knows that part, right? But the port numbers, some port numbers are well-known, at least up to 1024. This is all in 473 we teach. Up to 0 to 1024, these are standard, and they are well-known. So if you want to do HTTP, you generally do on port 80. But you don't have to do port 80. You can be on port 81, some are 8181, some people are 8080. Whatever port you want to choose as a provider, you can select. Right? The receivers have to, the other side has to know the same thing. So they can connect to you. Right? Because it is, at least right now, not possible to say that I want to connect to HTTP server. You just have to say a number. And that number has to be known to both sides. So there is a standard number and there are non-standard numbers. Okay? The same way here. Back to this. PSID is your port number. And a W-BSS is initiated when the first application registers and the provider service table is broadcast periodically. So basically, let's say an RSU, roadside unit, is providing two services. One is a best service, and second thing is, in general, they would be providing a map service or something, some kind of directory, business directory. So let's say providing two services, business directory and what did I say? Two services they're going to provide, so they will have two numbers. And those will be announced that, okay, I am here, and here is this BSS, and you can connect to the web service, and you can connect to this business directory. Right? And so people who want to get that information will connect to the right service. Now, before this announcement, they have to form a W-BSS. So as soon as the first application starts up, it tells RSU, look, I want to start a business directory, and so they'll start a W-BSS. They start announcing that, okay, I want to provide a W-BSS. Okay, and it will become a provider, and all the users will join that W-BSS. There may be another W-BSS which is providing some other service, and that is the provider for that service. And it may provide the same service also. It may provide a business directory service as well. But basically, the user has to decide which W-BSS to join and which service to join. Yeah. Yeah. No, they can be doing at the same time. It's just like this. Who can transmit the file? You can transmit the file, I can transmit the file. So it doesn't matter. You can do two applications at the same time. So you could be a W-BSS and you could be joining other W-BSS. If that's the question, right? Yeah. Yeah. So the thing is, it is quite possible that I'm getting my information from the roadside unit and I'm a big truck, police truck or whatever, or fire truck, and I'm announcing to the rest of the world. So I'm getting information on this side and sending it on the other side. Right? Huh? Like the AD. PBSS. Now, I forgot PBSS. In PBSS, actually, there were relays. And this example, the last example I gave was more like a relay example, right? But in PBSS, and the coordinator does not need to be, see, the thing is here, there are two functions of it. First of all, there is a coordination function and there is a service function. So I'm providing some information. And so for that service, I have to coordinate. Right? In wireless HD, the coordination function is totally independent. So if you're providing some service, you don't have to be coordinating. Okay, so let me give you an example. For example, if you have a DVR and a TV, DVR is providing the video, but it is not the coordinator. The coordinator could be TV. Right? And at the same time, the same network, somebody else, let's say a remote control, is doing something. Again, it is not the coordinator. It is just going to ask the TV when to transmit. Right? So, HD, actually, the service and the coordination, they're totally independent. Here, as soon as the service starts, it says, I need a coordinator. And it becomes a coordinator. Huh? Okay. All right. So let me say it again. Now the first one is, so the first service that starts makes that station become a coordinator. Right? If the second service starts on the same station, it's already a coordinator, so it doesn't have to start again. It just adds services to its announcement. Okay? Now there could be other, so it's like more like, and I can imagine, it's more like stores. You go to one store, it is selling groceries and clothes. Another store is selling medical devices. They are both providers. They are both services. They both have their own WSS. Right? So each service needs a WSS. If the station is already providing WSS, then it's fine. If not, then it will announce. All right. When applications register their interest with their WME, now user applications do the opposite. The user says, look, I'm looking for a service like this. They tell their management unit, WME, their management entity, and WME monitors announcements to check if the provider service table of a W-BSS is of interest, and that is trying to match. Is that this service available? Right? And when there is no active application, when the services go away, the W-BSS is shut down. If nobody is providing any service, the W-BSS goes down. Okay, so the main thing I think is that here the W-BSS are related to the service, which was not the case so far. I mean, access point, when you put the power on, it just starts. It doesn't wait for anybody to provide any service. It's always there, 24 hours, right? In this case, whenever there is an application ready and there is something to be done, then only we start the service set. And when there is nothing to be done, service set is closed down and there is no announcement. And I think this works equally well, and it saves some power because if there is no announcement, there is nothing to be sent out. I'm not providing any service, so the cars can just keep going by. They won't connect to me. Now, having said that, actually, I think if I had a roadside unit, I would probably provide a service called internet service. And many cars may want to connect to internet through this service. So they can always connect to 3G, 4G, whatever, right? But they can also connect through this one, which might be cheaper, through Wi-Fi, right? And if you provide a service like that, it probably will be up 24 hours. In the middle of the night, somebody comes and wants to connect to the internet, and they would be there. I mean, it could be 9 to 5 as well, but most likely it will be 24 hours. So anyway, this is all outside the scope of 802.11p. They don't decide on when you shut down, when you turn up. But basically, they allow the possibility that if you don't have any service to provide, shut down. Okay? All right. Now, how do the cars to cars communicate, right? And so that could be part of what we call, which does not require a basic service set. And so that is non-WBSS communication. So outside the context of BSS. So stations do not have a member of BSS to transmit. A DAVE device can send a WSMP message to broadcast address on CSE edge. On the control channel, you can say, I want to talk to somebody. Whatever you want to say. Another DAVE device can say, okay, all right, I'm ready to talk. And basically, you don't have to talk to each other. You don't need to have part of a BSS. So that is what it says, no WBSS synchronization. Timing advertisement from the providers, default parameters, values, and time stamps indicate local time, and authentication handled by higher layer. So basically what that means is that when you say I want to talk, you are the provider, and you provide the timing. You say, well, the time right now is so much in my clock, and this is what I will use. Just like a beacon, you just tell them that I'm going to use what kind of modulation, what kind of all other parameters that they need, and so the receiver will receive it and then tune to those parameters. So this is basically peer-to-peer. And security, etc. is not part of this layer, it is all higher layer. OCD stations use slightly higher AIFS than W-BSS parameters. Now, I don't know how many of you remember AIFS. Anybody? Yeah, interframe spacing, and that was in 802.11e, right? So that is the time that you have to wait before the channel has to be idle before you can transmit, right? And so OCD stations have to wait longer. So people who are using WSS, they in some sense get some priority. They're already scheduled, they already have coordination and so on going on. If they don't speak, then you can speak. OCD stations use wildcard in the BSS ID field in the MAC frames. And the BSS ID, which is actually, this is all 11 by the way, so it is still the same frame format with 4 addresses. In some of the frames you have BSS ID, and in the case of other, you will put the WBSS ID. Here you will put star. asterisk, wildcard. This could very well be all ones or all zeros. I don't know which one. But basically wildcard. So I'm not part of any particular W-BSS. So can you just see if you have any question about any of this statement here? No? One. So 11P, there are a number of companies which are making products. You generally don't see these products because these are sold directly to the car companies and they come directly built into the car if your car has a need for this. So OBU and RSUs, radios, SDR, software-defined radios, and then hardware implementation, HDL implementation. So ETM makes intellectual property. IP is there for intellectual property. Is that sometimes some companies, they don't sell any hardware, they just sell you a file, which is basically in this case is HDL implementation, hardware implementation of something. Okay, and then you can implement it. You can make the chip yourself. Card access engineering sells the designs. LightPoint makes the test platforms, and then there's spectrum analyzer, etc., etc. So some of these products are shown here. So GSRC is designed for short-range communications and good for city, but long-range communication is also required on highways using cellular technology. So GSRC does not really cover the whole VANET. It is only in the city that you can use it. When you get onto the highways, the distances become in miles, and the best way to use the cellular towers. These require multi-channel OBUs. And so the onboard unit will have to be able to use not only multi-channel, but also multi-network, which means that they have to be able to do 3G, 4G, and Wi-Fi. That brings us to the end of this module. And so the VANETs have a very dynamic topology, very tight delay constraints, and so now we know what is V2V and V2I, right? And we know what is RSU and OBU. Now they have only 10 megahertz, and therefore everything has been squeezed down from 11A to half in the frequency domain, and therefore twice in the time domain. Okay, frequency parameters are same, and basically frequency parameter number of players is same, and therefore in the time domain everything becomes twice. And then they have 5 channels. One is the control channel, and then 4 service channels. ASTM started with short message service protocol, and then 1609 started the MAC and the management, and then P provided the PHY, and they just basically took the 11A PHY, essentially. QoS is similar to 11E, but now extended to multi-channels. This is all basically the summary of this. There is a homework, and there is a reading list, Wikipedia links. Any question or anything?